Good day. Thank you for joining our webinar presentation on environmental disaster response. Today we're going to look at how data-driven geo-awareness can lead to faster and more accurate disaster assessments, better response decisions, and how ultimately help mitigate the impact of the disaster itself. We're also going to see how technology can be leveraged to inform those decisions. I'm Kent Watson with Textron Systems Geospatial Solutions. We're an industry-leading developer and integrator of advanced geospatial technologies. We've been providing products and support for nearly 25 years. Presenting today is Jonathan Gale. Jonathan has worked as a GIS analyst and a solutions engineer at Textron Systems. He is currently a senior geospatial solutions specialist and certified trainer. In addition, he teaches classes in LIDAR, radar, automated feature extraction, and geospatial intelligence for Northeastern University. Jonathan received the 2012 Textron Chairman's Award for Innovation. He has presented numerous papers on geospatial intelligence and automated feature extraction for diverse audiences nationwide. He lives near Missoula, Montana with his wife and 2 sons. We'll begin with a presentation on the topic of oil spill disaster response, its challenges, and where technology can best be leveraged. At approximately the bottom of the hour, we'll move into a question and answer segment before concluding remarks. However, we invite you to submit your questions throughout the webinar by using the chat capability. If you hover over the blue tab at the top and center of your screen, the chat icon will drop down. Just click on the icon and submit your questions. Also, if you must leave the webinar before the Q&A segment, note that everyone's going to receive a post-webinar email with both a recording of the webinar along with the contact information to submit questions and requests. So with that, let me hand things over to Jonathan.
Well, thank you, Kent, and thank you to everyone that's taken time out of their busy day to join us for our webinar today. As Kent said, we're going to be looking at using basically geospatial solutions for assessing disaster management issues. In this case, one that we're all familiar with, most likely the Gulf oil spill in the Gulf of Mexico in 2010. So what we're going to look at today is the problem itself, the potential solution, the case study example, kind of showing things in action, and then the results of the analysis that we've done from this for decision making, and then from there we'll open it up and have questions and discussions and so forth. So, getting right on with it, the problem itself, most everyone's familiar with this, the Gulf of Mexico oil spill disaster of 2010. The scenario we're looking at here is the movement of the oil is such that it's approaching the southern end of Louisiana near Timber Bay, and the need essentially is to utilize geospatial data to better coordinate cleanup efforts and the response efforts and so forth. And so remote sensing data and, in this case, automated feature extraction are looked at as possible solutions for assessing risk and basically communicating with response teams on the ground to more efficiently deploy resources and so forth. And so the solution we look at here, a little background, just as this disaster unfolded in 2010, the primary means for doing just this type of work was remote sensing and remote sensing imagery. So spaceborne imagery was used to monitor the slick. A number of other technologies were as well. And so in the case scenario that we're looking at here, we're basically going to task digital globe satellites for coverage for the area of interest. We're going to take that data and ingest it and define what our area of interest is, in this case Timber Bay and Grand Isle, Louisiana, that area. and then we want to identify the oil slick and compute the area of it so we know what we're looking at. We're going to utilize real-time weather and marine data as well to get an idea of the heading of the slick, where is it going, where do we need people, where do we need resources. We're going to create products essentially. We're going to identify, mark, and prioritize the communities at risk. We're going to publish a report, and we're going to share that with response crews via the cloud. That way we can collaborate and synchronize the information from the ground back to the shop, and then we're able to deploy resources accordingly. So as we're getting started, we're talking about data. Data is what's driving this whole process. Talked a little bit about digital globe. In this case, 8-band data, WorldView 2 data was collected. It's collected daily, and so this is the data we have available, dating from 2010, of course. So from the time of the accident itself, the format is NITF format. It's 1 meter resolution, and our area of interest that we're looking at covers about 10 square kilometers. In addition, we're going to utilize real-time data via Google Earth. We're going to work in a synchronized environment where we can utilize those resources and really add more to our map products, if you will. So with that, we can get real-time weather, nautical data, information on transportation, and cultural information about the communities that are at risk. So some of the benefits of 8-band imagery, which I think are important, number one is the scale in which you can work at. Spaceborne imagery is ideal for this. Again, NOAA, other agencies, BP, those who are involved monitored this primarily through these types of means, including digital globe. So you've got daily collections, so we can watch things each day. It's high-resolution data. We've got multiple bands to work with, which is very suitable for machine learning and automated feature extraction, just because we can manipulate the bands and basically isolate classes, kind of like you see here, that make the, I guess in this case, the oil, the vegetation, things like that stand out more in the imagery, and then it's much easier to collect with machine learning applications. Also with digital globe or with imagery, you have a web-based image service. So ideally, we've got our imagery streaming in. It's coming into a catalog where our data management is occurring, and that makes it so we're able to quickly query our data holdings. We've already defined our area of interest. So each day that we step through this, we have kind of a routine workflow in order to accomplish our goals or our mission. And so we're talking about remote sensing data, and you know, this is a geospatial problem in nature. So what are some of the benefits of approaching it this way and looking at the solutions that we're talking about today? Number one is just the efficient management of large data sets. In addition to that is the ability to visualize these large data sets, to put all the pieces together, define I guess a coherent area of interest, and put all of that together, including geospatial information, so that you can make informed decisions. With these products, you're able to create enhanced situational awareness. We're working in a 2 and 3D environment, so with Google Earth as well. So we were able to really develop a very detailed common operational picture. Our results are data-driven, meaning it's the data itself that is producing the information that we're using to make our assessment, to make our decisions. It isn't merely my interpretation or me drawing polygons around what I think the oil slicks are. We're relying on the data. So that's like some of the enhanced exploitation capabilities, being able to really drill down into the data. And then we take all this and we're able to put it in the cloud and share it in near real time. So all of this we can do very efficiently and rapidly. So as we look at our case study, our points of interest, again, are Grand Isle and Port Percheron. This is in this particular case where, based on our imagery and reports, that this is where the oil slick is closest to making it ashore. So already we have kind of a prioritized area of interest. So what are our objectives here? Well, we want to know the extent and the heading of the slick. We want to know what communities are at risk, how many people that involves. We want to identify, especially in this area, environmentally sensitive places, marshlands, things like that, beaches. And then by doing that, we'll know the number of acres that are at risk. We can easily measure or compute the length of shorelines that are at risk and add that to our report, prioritize and mark those areas that need immediate response. Logistics, we need logistics to know how to get people there. What is the quickest route in and out and whatnot, where are our resources. We're going to take all this information, compile it, publish it. That will be there for decision making, and then we want to capture the total time it took to do this entire workflow, because we're going to do it again tomorrow and the next day and the next day until this thing is cleaned up, essentially. So we develop a methodology for doing this. As I mentioned before, we have a stream of data coming in, so we need, I guess, an efficient way to manage that. So we're going to use a catalog function to ingest and organize the data. So once we've defined an area of interest, we can quickly query our resources or our data holdings and bring that imagery up. Next, we can take that imagery, pretty much tile it on the fly and create like a virtual mosaic, and then if it meets our requirements, then we can quickly generate that mosaic, put it into our viewer, begin to exploit it with automated feature extraction to extract the slick area. You can extract land area, water, basically anything that you can see in the imagery that will help support your analysis. But for the slick, we're going to compute the area using the area of the shape file that we produce. Again, we'll identify all the key entities and label everything. We're going to synchronize that with Google Earth so that we can get more real-time information to include in our report and in our analysis. And then we're going to publish everything back to Google Earth. So we have basically real-time, near real-time data, and we have that information out in the cloud where we can share that with people on the ground. And so how are we going to do this? We're going to start with REMOTEVIEW. REMOTEVIEW is kind of the imagery analysis powerhouse. It's able to handle huge data sets, manage them, manipulate them, has all the tools for basically going in and quickly annotating, putting graphics around things, and looking at variations in the imagery and so forth. Our catalog feeds right into REMOTEVIEW, so that's kind of seamless. From there, we're able to use supervised or unsupervised classification. We can synchronize in 2 and 3D so that we have that as part of our operational picture. And then whatever we're doing in REMOTEVIEW, that's kind of our base product, we're going to be synchronized with Google Earth. So whatever we're doing, the information that we're gleaning is going to be published to Google Earth, either on the fly or when we're done. We're going to publish, in this case, a PowerPoint. You have the ability to do 3D PDF, PowerPoint, a number of different products, and then you're able to extend that to a new application that we have called RV Cloud, which basically sends your map product out to a smartphone, and the person with the phone can basically add information, send it back, so that you're collaborating in that sense. So it's like having a REMOTEVIEW on your phone. Lastly, it's interoperable with ArcGIS. So we can utilize the GIS and a lot of the vector capabilities and GIS services that you can pull into ArcGIS to supplement this workflow as well. And next is Feature Analyst. Since we're able to connect to ArcGIS, our primary machine learning or feature extraction tool is called Feature Analyst. It's a third-party application in the ArcGIS environment. It is very much a GIS user's tool to rapidly create raster and vector products that are suitable to pretty much put right into a geodatabase, and that you can quickly edit and use for analysis. what we create in Feature Analyst has automatic attribution of the spatial data. So our attribute table has, I guess, all the important spatial characteristics. That's done on the fly. We can look at change detection, very useful with feature extraction. So in this case, we can look at things over time. Feature Analyst is model-based, so a process or workflow that we go through in training the machine to find the oil slick, we can turn around and use that model the next day. We can visualize it. If we had to train somebody, I can send it to somebody. It's very nimble in that sense, and then it can be used for batch processing. So there is an automated or semi-automated element to all of this to better help us streamline this whole process, especially with an event like this where the situation changes day to day. It's essential to eliminate some of these bottlenecks in the production cycle of things. And lastly, you can do distributed batch processing, which is the ability to handle huge stacks of data and farm that work out across a network. And RVCONNECT is basically what puts RemoteView and ArcGIS together. This creates a synchronized environment where whatever I'm doing in ArcGIS is basically syncing with RemoteView. If I'm creating with feature extraction layers, in this case the oil slick layer, then once it's finished it's going to publish or pop right into RemoteView as well. RemoteView is just, they're different tools, so RemoteView is just much better for quickly going in, putting a template around your data, doing measurements, annotation, and analytics and things like that, and then hitting one button and publishing. ArcGIS helps us on the production end in managing the GIS layers or the geospatial data that's going to supplement our imagery analysis workflow. So RVCONNECT makes that possible. It also allows you to use geodatabases, layer files, and other Esri products within RemoteView itself. And so this brings us to, I guess, the demonstration of all of this in action. What you see is the RemoteView interface. This will take us through basically the steps that were taken to make conclusions. So we're going to start by bringing in a topo layer, an open source layer. And so we can dial in that URL, and we can just open the map in RemoteView. So this gives us a frame of reference. We're going to zoom into southern Louisiana. And so we're basically drilling down into this, defining our area of interest. And we're going to find Grand Isle, our area of responsibility, ultimately. We're going to chip this piece of the map out. And by doing that, it will reload into RemoteView, and then we can use this for querying our catalog or our data resources. And so now we have the chip. And so we can take a point, our point of interest, so we get the geo coordinate. We can open our catalog now and search just for imagery. And so now we select bounding area, and we can plug in the chip that we just created, so that narrows down our search area. We can plug in the point that we just took from the map, and now we can query our records and look within a radius of, say, 100 miles, 50 miles. We'll do 50. And then we hit run, and that's going to search through all of our records. And so we'll get basically a grid showing everything that we have for that area. So we can zoom in, and the nice thing about this is we're able to select the different tiles in the grid and preview the imagery. So in this case, we can look, make sure that it's suitable. The catalog allows you to roam around, zoom, and inspect the imagery. And now you can just right-click and create a mosaic, or you can just open it right into the viewer. So you have 3 different ways to bring the imagery in. In this case, we created a mosaic on the fly, and now it's 8-band imagery, so we want to change the bands around so that we have one of the near-infrared bands. It gives us a little bit better contrast of our imagery, and it makes the oil slick more noticeable. And so now we're going to use RVCONNECT. We're connecting to ArcGIS. So the 2 applications are connected. I subscribe to layers. I can pull that image over from REMOTEVIEW. I can change my bands in ArcGIS as well. And so now we're going to use Feature Analyst Supervised Learning to extract this oil slick. Feature Analyst is really good at large land classes, just this type of scenario, especially if we can see it. So we create what's called a training set. REMOTEVIEW asks us if we want it over on that side. We don't need it. Change our symbology, something suitable. And then we basically begin digitizing polygons to provide the machine with the best examples that we can come up with for the oil slick itself. And typically, you'd want to do maybe a half dozen examples to start with. Feature Analyst has a preview function, so you can kind of digitize your training polygons just on a small area of interest and preview and see how it's performing. If the results are acceptable, then you can hit run, and then it's going to process the entire data set. The beauty of that is that you're not cranking out a bunch of shapefiles that you don't need and taking up space on your workstation. And so I'd say a high level of detail when doing this type of digitizing is one of the key parts of machine learning and supervised learning. You don't have to be absolutely perfect, but a few well-placed examples are going to get you a lot further than, I guess, some lousy examples. So now we can run supervised learning and do a preview on this. This is the nerve center of Feature Analyst. We can do one of the predefined settings. We can hit preview. This will give us a result in that AOI. It looks good, so let's run it, save it. Now that's going to process the whole image. Takes just a couple minutes. And so now we have our result. We can do a little bit of cleanup using an aggregation step. This will clean up bits of noise, pixelated noise. It'll consolidate the polygons, say in the wetlands and that. Again, we're trying to compute areas, so we want it to be a little bit more consolidated in that sense. And so now we're going to do what's called create vector metrics. This is where we apply area. Any of those attributes we can put into our table now. And then we'll add that layer to REMOTEVIEW. Check our attribute table. So there we go. We've computed area. We can do a quick summary. That gives us a number. So we've got our number there. So now the result is in REMOTEVIEW. We can annotate. We can build a template around it, and then we can put a grid on it. So now we've got product. How do we publish our product? Well, we can use PDF or PowerPoint. In this case, we'll start creating a PowerPoint slide deck. And so with one button, we can basically publish right to PowerPoint. We can zoom to different areas that we want to highlight, do some more annotations, push that over to PowerPoint, and continue to kind of build our report this way. And so to supplement our report, we can, we can also publish to PDF as well. So you get something like that. Lightweight, easy to send to somebody. And so now we can chip this scene out, and we can fire up the 3D viewer and not only visualize what we're doing here in terms of analysis in 3D, but from the 3D viewer we can publish products from that to our report or to send out in the field. And so this gives you the perspective of basically flying over the scene. It gives you an entirely different perspective of the oil slick itself. There's our annotations. Now we're going to push this to Google Earth. And so that sends our chip, our graphics, our annotations and everything. We've got that. And now what we can do is bring in real-time information to add to this, put it all together, and we've basically got our product. By this point, we've marked the beaches and things like that. We know where the oil slick is. We can look at the loop current here. We can get this product. We can figure out the direction. We can bring in a weather product. So now we can see precipitation, radar for this area of interest. We can check the wind speed, tides, any of those things. Now we can add a marine traffic layer. This will tell us, you know, Port Fourchon is probably one of the busiest oil ports in this area, so there's going to be a lot of marine or ship activity in this area that we want to be aware of, so to speak. So we put all of this together into our report. We've defined our area of interest. We've created a mosaic and a processed mosaic of the area. We've defined the area of responsibility. We've got our products here from REMOTEVIEW showing our areas of concern and risk. We've incorporated real-time weather, current information, marine traffic, and then we can bring in population information to give us numbers on how many people live there, cultural information, things that we need to be aware of, bring in logistics as well, put all of this together and create our dissemination of findings. And so, in doing all of that in a quick few minutes, what did we learn from all of this? Based on the analysis, the extent and the heading of the slick is, well, our AOI is about 10 square kilometers. The extent of the slick is about 3.8, so it's about a third of the scene or the imagery mosaic that we created. Based on our weather information and our real-time current information, we can estimate that it's moving 1 to 3 kilometers per day, east-northeast, or 1 meter per second. Communities and total population at risk, we've got Port Fourchon, first and foremost, with the most people and the most activity. So that's how we're going to be able to prioritize. Grand Isle would be next. There's a lot of beaches there, 2 different types of communities. One's a little more industrial, one is more residential, but approximately 341 persons per square kilometer for this area. The environmentally sensitive areas that we've identified from our maps, from Google Earth and that, are Timbaler Bay, Caminada Bay, East Timbaler National Wildlife Refuge, and Grand Isle State Park. So we're going to want oil booms, we're going to want crews. These are nice beaches through there, so it's important that those areas are protected. Total number of acres at risk that we estimate is over 1,000. We did that by, we can measure the beaches. The length of shoreline, we measured that as well, about 26 miles of shoreline at risk that we need to be aware of. We've prioritized our areas, Grand Isle, the Elmer's Island area, which has most of the beach that we're concerned about, and then Port Fourchon itself, which is not necessarily a beach community, but an oil port, so to speak. The total time for this is, we're saying, an hour and a half. Really, it's much less than that. Most of the time is probably spent upstream, basically bringing in the data and setting up the ingest so that your feed is coming in right into your catalog. Once that's set up, as you saw in the demonstration, it's pretty much getting started, bringing in your imagery, defining the area of interest, exploiting the data, performing your analysis, and then publishing your results. So all in all, a very efficient workflow. Many of these steps can be automated and streamlined, and the idea is that we can take this and apply it the next day or each subsequent day as as the disaster unfolds or continues to change over time. And so that brings us to everybody's favorite part, the questions and discussions.
Thanks, Jonathan. That concludes the presentation portion of our webinar today. We're now going to move into a segment of questions and answers. Again, to ask a question, hover over the blue tab at the top and center of your screen, and the chat icon will drop down. Just click on that icon and submit your question. And as we wait for our first questions, let me just say that subsequent to today's webinar, you'll receive an email containing a link to the recording of this presentation. And the link will also contain, or the email will also contain information by which you can contact us if you have questions or communications that you'd like to pursue later. Now let's take a look at our first question. It looks like it's a question, Jonathan, relative to level of effort. In essence, this looks to be a sophisticated geospatial environment. You know, what generally does it take to get this up and running? Can you comment on that, Jonathan?
What we saw today is, you know, if you have the data, digital globe data deliveries are pretty straightforward, especially if you can stream them right into your environment. Setting up REMOTEVIEW is, you know, basically an installer. We install that on our desktop machine. If we have ArcGIS, we can install Feature Analyst, and then that becomes active as an extension in ArcGIS. The interoperability piece, RVCONNECT, same as, it's like a third-party extension as well. So those guys, you know, show up in REMOTEVIEW and in ArcGIS. So it's, to do what you see today is 3 installations, all of which can be downloaded online anytime. Feature Analyst can be demoed for free, and it has a tutorial that comes with it that teaches you the basics, pretty similar to what we saw here today. Gets you up and running, and then with Feature Analyst we offer 7-14-day evaluation periods where you could take data and work with it yourself. We can arrange similar type of setup for REMOTEVIEW as well. So any of this can really be evaluated if someone is interested, and we're happy to provide information on how to get started doing that if you needed that.
It looks like that's it for questions at this point. Jonathan, your explanation and presentation was very thorough. However, again, if you have questions that come up later, please don't hesitate to call us. That's all for today. Thank you for attending, and have a good rest of your day.